Traditionally, we think of cyclic cosmology models as implying the current expansion of the universe will reverse, recollapse under its own weight, and then bounce back. But is it possible to have a cyclic model from a universe that never recollapses and is instead, in some sense, always expanding? Roger Penrose has proposed just such a model. In one of our earlier films, we discussed his conformal cyclic cosmology. But new developments in the field have led us to revisit this fascinating model with some of the scientists who have worked on it, including Roger Penrose, Maciej Dynowski, Krzysztof Meissner, and Paweł Narowski. But for those that didn't see our previous film, let's recap. What is CCC?
Conformal cyclic cosmology, or CCC as I sometimes call it, is a cosmological scheme which I introduced in about 2005, sometime around then, which has, I talk about things which are called eons. Now our present eon would be starting with the Big Bang, the universe expands, and then it goes into this exponential expansion, which is fairly recently observed, and then that goes on forever. This remote expansion is physically equivalent to another Big Bang. And our Big Bang was the continuation of the remote future of an exponentially expanding previous eon. And the idea is these eons go on and on and on forever, in both directions.
How can the future of an expanding universe be equivalent to the Big Bang? The answer lies in a type of geometry known as conformal geometry. Conformal geometry is concerned with shapes irrespective of their size. So consider a triangle. You can say that its angles sum to 180 degrees, even if you know nothing of its size. Or imagine we stretch this small chessboard so that it's the size of this large one.
Now, the chessboard becomes very large, but you would still have 64 fields on it, and you can say which is first, which is second. And the angle, if you look at it correctly, the angle between the corners would still be 90 degrees, even though you've stretched it. But this geometry goes much deeper than that. What you're allowed to do in conformal space is to stretch things differently.
Conformal play, then it will be like this, that you will lose the time of particular move, but what you will have ratio of the distances between particular pieces, and you will have ratio of times between particular moves.
A chessboard, of course, is a conceptual thing which could be big or small. You see some big ones in parks sometimes, and you see little tiny miniature chess sets, and it's the same game. That's the point, that it doesn't depend on the scale of the board.
Conformal geometry preserves angles while losing the notion of scale. But what has this to do with the evolution of the universe?
And Einstein tells you that mass and energy are equivalent. Planck tells us that energy and frequency are equivalent. That tells you that mass and frequency are equivalent through these two very basic laws. That basically tells you that any stable particle which has a mass, massive particle, is a clock. So if you want to measure geometry, you use clocks. Okay, you have good clocks if you have mass, but if you don't have mass, you don't have good clocks. And there are two places where it can be argued you don't have mass. One of them is in the Big Bang. So you go back and back in time, and you get to the Big Bang. Now the thing is that the Big Bang is extremely hot. It means that particles are racing around at a great speed. When you get nearer and nearer to the Big Bang, you find this speed is so enormous that the masses of particles are completely irrelevant.
Once all matter in the universe is swallowed by black holes and the particles lose their mass, which is one of the assumptions, controversial assumptions of the CCC model, there are no massive particles left and no physical clocks. And what Roger argues then, it only the conformal geometry which matters,
So the claim is that the physics in the very remote future loses track of scale. So the big and small become equivalent. So that's the thing that's hard to get your mind around. You see, how is it that this very big, cold, rarefied universe can be equivalent to a very hot, dense, smaller, universe? But they're physically equivalent if you don't have a scale.
Penrose and Hawking had previously shown that given certain assumptions, there must be a singularity, a point of infinite density and curvature inside a black hole and at the Big Bang. If CCC is going to give us an eternal universe, it must remove the singularity at the Big Bang.
Penrose first and then Penrose and Hawking proved together is that these are very generic evolution behavior of any state of matter. Whatever you start with is likely to collapse to a singularity. But these theorems really assume that you have a matter content of a universe, whereas what's important in the conformal model is that you don't.
The most important object to describe the space-time is space-time interval. It tells you about distances of events in space-time. And now this space-time interval, mathematicians and physicists encode is something which is called metric of the space-time. The metric is determined by 10 functions, which are 10 components of this object which is called metric.
Singularity of a collapsing star is, we would say, much more messy. All components of the curvature tensor, which measures how curved the space-time is, blow up, are infinite. In the initial singularity, the Big Bang singularity, only one component does, and that can be regularized, fixed by changing to a conformal geometry.
So what is singular in Big Bang is only this one function, which is actually a scale. But scale has meaning in Lorentzian geometry, but it doesn't have any meaning in conformal geometry. The singularity at the Big Bang is only singularity of one function which is actually not relevant at all to describe conformal geometry.
So by allowing yourself to stretch a metric at the point of the Big Bang, you can make it regular. What the conformal cyclic cosmology model does is then matches the metric at the end of one eon to a metric at the beginning of the other eon, in a way that the transition is smooth.
It turns out that conformal curvature of black hole is infinite, whereas conformal curvature of Big Bang is just 0.
Conformal geometry removes the singularity at the Big Bang and allows us to look at what happened before. But perhaps its biggest advantage is addressing two mysteries about the entropy of the early universe. Firstly, why was it so low at the Big Bang? And secondly, when we look at the oldest light in the universe, the cosmic microwave background, why is it a thermal blackbody? Isn't that high entropy?
Now there's a sort of seeming paradox here. It's what I call the mammoth in the room sometimes. When you go back to where the entropy ought to be as small as it could be, you find evidence for the entropy being as large as it can be. Now, it's not a contradiction because this is only taking into consideration the radiation and matter. It's not taking into consideration gravity. Now, gravity sort of works in a different way from other fields because you also see from this cosmic microwave background, or the CMB, that the radiation is very uniform over the whole sky. And so that also is an indication of high entropy if you're thinking about matter and radiation. But gravity, it's low entropy, because gravity proceeds by, say, take a uniform distribution of mass, and then it clumps. You produce regions of high concentration, and then stars and galaxies, and it's this going towards this lumpy situation, which is where the entropy is increasing. So the uniformity that is observed means low entropy in gravity. If you scale down this remote future, you get something which looks very much like the Big Bang which we see. Now, here's the main point of the story, is that the way gravity scales is such that it's killed off. So that is to say, any gravitational degrees of freedom which were there in the previous eon, in this very rarefied, expanded case, when you squash it down, they're not there. So the gravitational degrees of freedom are wiped out. When I say degrees of freedom, I mean the number of numbers you need per point to define what you're talking about. And so this scheme automatically gives you the low entropy in gravitation that we need in order to set the second law off in the way that we see it.
Conformal cyclic cosmology can explain then why the entropy of the Big Bang was so low. But in order to do this, it must assume that information is destroyed in black holes. Most of the entropy of the universe is contained in these incredible objects, and if they destroy information, then when they evaporate, the information about their entropy will be gone too. This seems to be the inevitable outcome of general relativity. But quantum physicists have another principle called unitarity, which seems to point to the opposite conclusion.
Unitarity tells you that probability in quantum evolution has to be conserved. So probability doesn't disappear. The information loss in a black hole would violate such probability conservations. So the particle physics perspective is that there isn't such loss. The information is recovered. How is it recovered? Nobody knows. There are various models being proposed as we speak. I think it's the verge of a philosophical dispute whether you regard quantum theory or general relativity as more fundamental.
Quantum effects stretch over huge distances. Sure, they do. But there's virtually no mass in any of these experiments. If you displace mass, you see, quantum mechanics says, say, if you've got one thing can happen or another thing can happen, then you could have this and this happening together. Sort of weighting factor between the two, but they're both there. That's the Schrödinger's cat thing, you see. Schrödinger was pointing out the absurdity of this, of his own principle, you see, saying, okay, you could have a system where a cat could be dead and alive at the same time. That's a load of rubbish. There must be something wrong with my equation. That's Schrödinger's equation. Well, he didn't quite put it like that, but that's more or less what he was saying. There's something wrong with quantum mechanics. And it seems to me clear. There's got to be. Whenever a measurement takes place in quantum mechanics, you throw unitarity out the window, you wheel in something else, use that, and then wheel it back, and then wheel unitarity back in again. The way you use quantum mechanics is violating unitarity all the time. But people sometimes say, oh, well, you're not really, you must be doing something very subtle instead. It's blatantly violating unitarity. And for some reason, people just don't accept that. They just say quantum mechanics is so well confirmed, but only at a level where I would say, sure, you expect unitarity to be confirmed at these levels. Yes, of course. It's not disturbing the geometry enough. It's not coming into a place where principles of general relativity are running you into trouble.
If you think that, like Roger Penrose does, that quantum theory has to be modified in a way which takes mass into account, you'll be quite relaxed to let it go and to agree that information is lost in a black hole, and that is what the CCC model requires.
Experts in general relativity, Kip Thorne and Stephen Hawking, bet quantum physicist John Preskill that information would be lost in a black hole. In 2004, Hawking conceded that Preskill was right, that quantum physics could show that the information would be preserved. Kip Thorne refused to concede. If an astronaut crosses the event horizon, he should not notice anything unusual. But if the information is preserved, it seems he would burn up in a firewall, which violates a basic principle of physics known as equivalence. This implies that the solutions to the black hole information paradox are not quite as sound as was thought.
Okay, if they run into firewalls, well, yeah, I told you so. I mean, I didn't tell them so because I didn't think about firewalls, but I mean, it's the sort of trouble you run into if you insist that unitarity should hold at that level.
If CCC is right, then it solves a deep mystery as to why the entropy was so low at the Big Bang. But many people have quoted Roger Penrose as implying that this is the most extreme example of fine-tuning. Cosmologist Sean Carroll has argued that it is not fine-tuned for life.
It's pretty gross, coarse tuning. The entropy in the gravitational field is ridiculously small compared with the the entropy in matter. There's nothing fine-tuned about it, it's just huge.
What you were saying was, people had argued there are these constants that's fine-tuned for life, and he said, well, hang on, look at the entropy, that could be much, much higher, and life would still be here, so that's not fine-tuned for life. Therefore, we see something that clearly isn't. Would you agree with that?
I absolutely agree with that, yes. The entropy could, in gravitational field, could have been far larger without disturbing life as far as I can see. That's something I agree with.
CCC implies that the low entropy of the Big Bang was not chosen at random, but forced into a low state by conformal transformations, removing the gravitational degrees of freedom of the previous eon. In order to demonstrate how unlikely it was that the entropy was chosen at random, Roger Penrose has been quoted as saying, "This now tells how precise the Creator's aim must have been, namely to an accuracy of 1 part in 10 to the 10 to the 123rd power." Unfortunately, some people have taken this a bit too literally.
I hope it was, if people read my book properly, they wouldn't have thought I necessarily believed in any being who created us. I don't think that helps much. I mean, a being in the sense of a conscious being or something that the word God is applied to, is not the view which I hold to. I mean, that's just a metaphor. I'm using a picture. I like to draw this picture of this. There was a nice story about that. I've given a lecture with this creator, a picture that I use in The Emperor's New Mind. And somebody in the question time said, in your picture of God, why did you depict her with a beard? So I said, I brought my picture up again and said, well, if you look carefully at this picture, you will see that there are 2 interpretations of that beard. One is it's a beard, and this is a man, sort of god, male god, or that this is hair coming around, and it's a female god. I was completely neutral about which gender that creature was. But to say it's a being of any sort, that's a joke. I mean, I like to draw these pictures, and to have this image is a very useful one. And I'm amused when people pick it up and try to say that I'm claiming that there is a creator out there. That's not my view at all.
Even if the low entropy state of the universe was not fine-tuned for life, many have argued that other constants are. In inflationary cosmology, this can be solved because it seems to generate a multiverse. But CCC is an alternative to inflation. So how do its proponents respond to the issues of fine-tuning?
So one view is that, okay, there are lots of these parallel universes, and in each one of them you've got different constants of nature. And okay, the ones with the constants of nature just coming out right, okay, that's where people are. So you have beings of the kind we know in this universe, but not in that one. And the reason we're in this universe is because we're people, and people have to be in the universe that they could be in, you see, well, sort of tautology. Well, CCC is a different picture. It's a sequential. You say there are different eons, one after the other, but not next to each other in this other sense. And one possibility might be that in the eons of CCC, these numbers have different values. And there's this thing called the anthropic principle, which might say, well, we're only in that eon where these numbers have exactly the right values, where life could come about, and if you monkey with these numbers too much, life wouldn't happen. Now, I think that's it's a bit of a dangerous argument because we have no idea what life would be like, even with these numbers. We don't know enough about life to know that it would never necessarily come about with the numbers that we see. We don't know enough about it to say it wouldn't come about with other numbers. So I think it's a dangerous argument to use. There may be another reason why they have these values, which is purely mathematical. We just don't know. So there are big questions here, which are interesting to talk about, but I don't think you can make any big conclusion from them. And it's certainly quite a possibility, and it's what emotionally I would say I would like the best, that somehow there is a mathematical reason that the universe, as we know it, comes about because these numbers have those values mathematically.
We have absolutely no clue whatsoever into why the constants are what they are. No clue whatsoever. I would rather think that they are solution of some equation that we don't know, and they have to be what they are at some point, and not that they are randomly chosen, because then I would say it is extremely bizarre that they do not change within our universe. I would love if any theory makes the observable physical constant necessary and not accidental.
And that's a plausible option?
That's an absolutely plausible option, and I would be absolutely happy to see such a theory formulated.
The standard model of particle physics is incredibly successful in describing the structure of atoms. But astronomers tell us that most of the matter in the universe is not made of atoms. Instead, it's dark matter, which is nowhere to be found in the standard model. Another potential strength of the CCC model is its ability to address this mystery.
People these days worry about these two things, one dark energy and the other dark matter. Both are very bad terms in my view. Dark energy particularly because it's not dark, it's invisible. And it's not energy, it goes the wrong way because energy is attractive and this is repulsive. So it's a funny kind of energy, if it's energy. But never mind. The dark matter is only, it's matter all right, but it's not dark either. It's invisible. Okay, fine, that's just a quibble. When you do this to go from your remote future of the previous eon, squash down to the Big Bang of the next, and you write down your equations, you find that there has to be a new material which is a scalar. That means it doesn't have a direction quality, it doesn't have any spin, it's just a number which tells you how strong it is. And that field has to be there. Now, you don't want that stuff to build up because each time you go through a cycle you produce new stuff. So this means that it has to decay. So right from the Big Bang it starts to decay away. And it decays away until it's all gone by the infinity of that eon. Now in its process of decaying, that's what we consider is the source of these fluctuations in the spectrum. The people, see, in the eon after ours, when they look back and see their cosmic microwave background, they will see, oh, we see this scale invariance and so on, as we do. And this scale invariance, according to me, is this, I should say this is a scheme worked out between Krzysztof Meissner, who's a Polish scientist who's been working on CCC for a lot, and he's a colleague of mine, and we have this idea that it's this decay of the dark matter.
You look how curvature just before the bang is expressed by the curvature just after the bang, or you can do the opposite, see how curvature after the bang is related to a curvature before the bang. And that depends very much on what these conformal factors are, these stretching factors. What a miracle seems to be happening, a combination of these conformal factors, technically speaking, you have to divide one by another, satisfies the equations one would expect from a scalar field modeling the dark matter. So they really arise very geometrically from conformal geometry, conformal changes of the eons. This was proved by Paul Todd in the last 4 years.
Dark matter seems then to be an inevitable outcome of CCC. And Roger Penrose has dubbed associated dark matter particles erebons after the Greek god of darkness, Erebos.
Now, it's appropriate because he's not only the god of darkness, apparently, but he is a primordial god, so he's right there at the beginning. So this is just perfect as far as I can see. So these particles, I call erebons, they would have something like a Planck mass, so within a couple of orders of magnitude, I don't know to be quite sure about this, and a decay time of something like 10 to the 11 years, so a half-life of something like a 10 to the 11 years. So that's a bit longer than the current age of the universe. But even though it's an awful long time, since these particles dominate the matter in the universe, their decays, you should be seeing them now. So my view is that the erebons are behaving like classical particles. And so when they decay, the signal that they emit would be basically a classical wave. Now this wave would probably have some kind of very high frequency. Because of this very high frequency, all you would see would be the energy content of this wave. So it would be like an impulse, which could in principle affect gravitational wave detectors.
Recently, it's been claimed that the gravitational wave detector LIGO has detected something that might indicate the existence of error bands.
I'd just given my talk in Vienna and mentioned possibly that LIGO, maybe in its rubbish bin, would have evidence of signals of this nature. I hadn't gone through it or calculated what they might see or not, but it was just a suggestion. And then very shortly after that, I was told that there had been a bit of a controversy because people in Copenhagen, a group there, what they did is they looked at the little pieces of data which had been released, which was only just around the actual signals. But if you look at the noise in those signals, not the signal itself, but the other things which are considered to be irrelevant, just some kind of noise, they find evidence for correlations with the same time delay in the noise. So that night I found myself having difficulty getting to sleep because it seemed to me possible that what they are seeing is not just some artifact which doesn't mean anything, but maybe the error band decay from the galaxy in which these black holes are. I submitted an article to the archive making this suggestion, which I wasn't really sure about, but it seemed to me an interesting thing to pursue. And there was a little bit of a discussion by this in the blog by Sabine Hossenfelder. And she likes to be critical of people's theories, and I think very sensibly often. And so she made some comments about what I'd said, quite sensibly, I think. Were the signals strong enough? Why doesn't one see these from our own galaxy, for example? I thought about that a bit. And what kind of signals are you seeing? Are they strong enough from a distant galaxy? And I said, well, no, you're probably, what you'd have to see is some kind of average effect, but some kind of wiggly random shape, which you might correlate between the two things. And then she got back to me and said, oh, you mean HBT? And so I got back to her, well, I don't know, what's HBT? So she got back to me and said, oh, Hanbury-Brown twists. And I said, Hanbury-Brown, I knew as a scientist, he did a very interesting series of measurements on stars to measure their diameters. And what he and Twist did was to look at electromagnetic signals, and they're looking at them quantum mechanically. So these are individual photons, and they are looking at the correlations that you tend to see, and could they get any information from these interference. And they got into a lot of trouble from a lot of famous physicists, apparently. Said, no, you can't get interference between different photons. The photons only interfere with themselves. And they say, no, this is what we're seeing. And it turns out they were right. And so Hanbury, Brown, and Twist were using this effect to measure the diameters of stars. And they did this very successfully. They were able to measure the diameters of quite a number of stars in these old times when people had no very good measurements of this nature. And but this is the Hanbury-Brown twist effect. And what you tend to find is that the bosons coming from the star, which this photon coming from here and this one coming from here, they are entangled in a way, and it makes the signal clumpier than it would be otherwise. But if the Hanbury-Brown twist effect is operative here, quite possibly you would be able to see a signal which it would be a random signal, but the same random signal seen by the two detectors. Now, I'm still thinking about this. I have no clear idea whether something like Hanbury-Brown twist is actually what's happening here.
Roger Penrose and Vahe Grisadian claimed to see circular structures in the cosmic microwave background. They suggested this was caused by gravitational radiation emitted from black hole mergers in our previous eon. Many CMB cosmologists said this was just noise. It's this that Christoph Meissner and Pavel Murawski have addressed.
In order to check if it is statistical fluctuation or not, I should have another maps of cosmic microwave background radiation. But I cannot have another maps because we have only one universe, so there is only one map. So then the question was how to create such maps that imitate the universe. And I didn't know how to do it, and I had no idea. And I met my friend Christoph Meissner, who told me that he was actually thinking about such a problem for totally different physics related to actually searching for Higgs boson. So he had similar problem in particle physics, and he actually said that he knows how to solve it.
We created 1,000 artificial maps that reproduce these general statistical features, but of course that we are sure that there are no ring-type structures that are encoded into those pictures, into those images, because they were purely statistical. In that way, we compared these 1,000 artificial maps. What is a probability of finding of a given ring-type structures on maps that we know do not have encoded ring-type structure? Then we looked with the same algorithm on the actual, true, real Planck map. It turned out that the 999 maps performed worse than the real map. So the probability of finding structures there, only on one map out of 1,000, it looked like had more ring-type structures than the real map.
Statistics is a tricky business. If the circles on real maps were statistical fluctuation, they should behave like on statistical maps, but they don't. So I would say that they are real.
We have now only one system, one map. So it is different from particle physics, because in particle physics, if we want to check something, then we collide the proton with proton billion times. If we are not yet convinced, we collide it for another billion or 3 billion times, and so on. Of course, the invoice comes with billions of Swiss francs, but at last we can be convinced with arbitrary statistical precision. It is not the case here. We have here only one map, and it is slightly a matter of prejudice whether we say that 999 maps which perform worse than the real map is some kind of a quote-unquote proof that these ring-type structures are there as real structures or not. One can say, okay, it may happen that purely statistically real map performs in such and such way, but it's purely statistical. So there are no means of actually convincing someone who has the primordial assumption nothing is there. It's purely statistical, purely Gaussian. Whatever you see is purely statistical. We cannot produce 1 million other real maps to say, look, that's what we have. But one has to be careful. If we imagine that someone comes to the Earth and makes one photo of a night sky and comes back to some alien civilization and shows with this one photo, there is one circular object shining on this photo. And if someone said, if there are 2 or 3, then we would believe. But since you have only one photo with one circular object, probably it's the statistical fluke. That would mean that they would miss the moon.
They have different definition of the circles. So they are talking about different things than we are talking. They are using different statistical maps. Actually, we wrote 2 papers about these things, about searching for the circles. The first one was, we're using our created maps, our statistical maps, which we believe are absolutely beautiful. That's a work on its own, that we just found our own method of creating these maps. Then we were criticized by astronomers that actually we should use statistical maps that every astronomer is using, because otherwise we cannot compare. Our second paper was using statistical maps as astronomers they use. So it is their maps. And we still have our conclusion.
There is a paper, a Canadian paper, where they repeated the analysis that Vahe Gerzajan and I did on the WMAP data, and they do find pretty well exactly the same patterns that we claim are there. So you see concentric sets of low variance circles in the same places, in the more or less the same numbers that we found. So that seems good evidence. They do, in their paper, the Canadians claim that this is probably just a random effect and not, anything to take seriously. What they don't comment on, though, however, is the very, very strongly anisotropic, or inhomogeneous, I should say, a very highly inhomogeneous pattern in the sky. So you see certain regions, the centers of these circular rings, are clumped in very particular regions. And this is very hard to see how anything like that could come about from the conventional explanation, because the conventional explanation for variations in temperature in the cosmic microwave background are random effects, what they call the inflaton field, which is what makes inflation go in the inflationary scheme. You have random quantum effects, completely random, and these produce these temperature variations. Now that means that it ought to be random over the sky. Why are they concentrated in very, very localized regions? Now, we didn't expect that either. And this would mean that in the previous eon, according to CCC, in the previous eon, there were very, very super duper clusters of matter, which are not very uniform. Now these would be clusters of galaxies which have big or lots of supermassive black holes in them. Maybe there's something else which concentrates them in some regions. But the most natural explanation is that there's more matter there.
Since we made our first film on CCC, a telescope at the South Pole claimed to have found a type of polarization signal known as primordial B modes. These are claimed to be a smoking gun for inflation. However, further analysis showed that the signal was ambiguous and could simply be from dust in our galaxy. But many scientists are looking for these B modes. What if they are found?
Now, when I first heard about the BICEP 2 observations, I was a little bit worried because it seemed to indicate, as they claimed, the presence of primordial gravitational waves, so gravitational fields in the very, very early universe without a source in the ordinary sense. Now, CCC doesn't want that because CCC claims that the gravitational degrees of freedom are essentially wiped out. The evidence that the BICEP 2 people had claimed seemed not to be as strong. People say, well, no, the evidence seemed to be, it could have been dust or something, which is creating the effect they see. I think the argument at present is that it could have been dust, but it's not clear whether it was dust. I have a colleague, Paul Todd, who was very central to the development of CCC. It was one of his ideas, in fact, which started the whole scheme off. He put to me at one stage, would it be possible in CCC for magnetic fields to get through from one eon to the other? And I'd say, yes, certainly. Magnetic fields, that's photons, that is massless things. They wouldn't even respect the scale and change. They wouldn't even notice. So there are regions in space where there are no galaxies. They're just empty, as far as one can see. And in these empty regions, there are observed magnetic fields. And where do they come from? So they presumably came way back from the very, very early universe. So there is some evidence that magnetic fields have been around for quite a while. Maybe they could have been there from the previous eon. And if magnetic fields are around in the early universe, they could also produce these B modes, which are the things that the BICEP 2 people claim to see.
In our previous film, we presented Sir Roger with criticism from philosopher William Lane Craig. Craig was recently named 11th most influential philosopher in the world. Craig claimed that CCC is a multiverse model with parallel universes emerging from a single point. Sir Roger said this is false. The CCC model is not a multiverse model and is likely eternal into the past. Dr. Craig devoted an entire podcast to respond, claiming that it's meaningless to say that one eon is before another. So let me quote you the criticism that we've read. You can't really say that these universes that are stacked up are sequentially ordered in time. Rather, there is time in each universe that runs from the Big Bang to infinity, and there isn't a kind of hypertime in which these are all then sequentially ordered. He was very interesting in the interview with Penrose. Did you notice what he said? He said, as you go into the past, there becomes a time at which mass first becomes relevant. Then he says, before that, Mass was not relevant, and so there was no time. On the face of it, that is logically incoherent. It is logically incoherent to say before that there was no time. So how do you respond to that?
I'm afraid this is a misunderstanding.
I think that is misunderstanding.
No, this criticism is based on some misunderstanding.
The conformal picture, there's still a notion of before and after. The causal relationships are unaffected. That is to say, if A is before B on, say a world line, then that means, suppose you have a particle, and it could be a photon even. And then the photon's history, you think of as a line in space-time, it still has a notion of which is prior, which event on that world line is prior to which other event. So there's an ordering. There isn't a scale which tells you, how many seconds there is between this and this. There is still a temporal ordering. So I think the criticism is simply a misconception here.
I don't think that's a valid criticism. Let me explain why. In geometry and relativity, we talk about something we call the causal structure. That tells us what happened before and what happened after, which events can cause other events. The way this is described in special and general relativity is by a notion of a light cone. See, nothing can move faster than light, so we could only have been causally affected by events which took place in our past light cone. You then have to think what happens with the light cones in conformal geometry. Well, what happens is the following. The notion of distance or time is not really there. However, the light cones haven't changed. That's the whole point of conformal geometry, but they don't. The null surfaces, trajectories of photons stay the same. Although the geometry inside the light cone and outside the light cone have been distorted, it's still, because of continuity of space-time, meaningful to say, in conformal framework, that something was inside or outside the light cone. So the causal relations haven't been distorted. I think we can go a bit further than that. It is claimed in the conformal cyclic cosmology models that some events which took place in the previous eon directly affected what happened in our eon. So conformal geometry, whilst it gives up a distance, it has still this causal structure preserved, and you can make sense of before and after.
So to say that there is no time, so we cannot say whether one is after or one is before, it's a misunderstanding, because in the next eon, massive particles would look backward into light cones, backward light cones, and would see suddenly the traces of a collision of a black hole. So the notion of time is very well, let's say, settled.
The main criticism, if I use the word no time, what I meant is there's no scale of time. It's not that there's no time. There's another point I should make, though. It's quite useful to talk in terms of a conformal time. You see, there is a way of introducing a pretty good notion of time, which is not the ordinary scale of time, but it's in a conformal diagram. You scale everything so that the speed of light is drawn in the picture as the lines were 45 degrees. And then you can measure up in this picture. And that's useful to say when something happens on this conformal time. So the conformal time is not measured in seconds, but it's measured as there is a way of doing it in a perfectly good mathematical sense. So there's nothing wrong with what I said. It just involves notions which you can't just dismiss by saying, oh, there's no time, so it means nothing. I'm afraid it's misconceived.
Maciej Danowski investigated CCC looking for something called cosmic jerks and snaps.
When the CCC model came about, I was interested in how observable, or in principle observable quantities, which one can measure, how they change from one eon to another. What are these observable quantities, cosmic scalars as we call them? I mean, the standard cosmology, and which is accepted both by inflation models and by CCC, consists of a very simple solution to Einstein's equations, which we called FRW spacetime. And what an FRW spacetime is a sequence of three-dimensional spaces with some time-dependent scale factor. What Einstein's equations then do is they tell you how this scale factor changes. Now, out of this scale factor, you can construct objects which you could measure, and some of them have been measured. You can see how it changes in time. That gives you what's called Hubble, and measurement of this Hubble constant was one of the milestones of general relativity. The next one, mathematically, the second derivative of this scale factor, it's called deceleration. So whether we decelerate or accelerate faster. You can then ask about higher derivatives, so how a deceleration changes in time. That in mechanics physics called jerk. So a jerk is a change of acceleration. Well, if you're happy with jerk, you might go on. The next one is snap. There are some estimates now on how jerk changes in the universe. We think that jerk for our universe, our matter model, is very close to 1. Snap hasn't been measured. I then moved on to compute these cosmic scalars for the simplest case of conformal cyclic cosmology model just before the Big Bang, so at the late stage of the previous eon and after the Big Bang. And I computed how they changed. And amazingly, they all change together, but in a way which makes the conformal Einstein equations invariant in agreement with Roger's proposal.
In one of our previous films, Stephen Hawking and colleagues explained how introducing complex and imaginary numbers, for example, the square root of -1, leads to changes in how we understand the physics of the early universe. So Roger has also been fascinated by these numbers, which led him to the development of Twistor theory.
I was amazed when I first heard that quantum mechanics does involve complex numbers, square root of -1 and all that, at a fundamental level. And it's involved in this idea of the superposition principle in quantum mechanics. This is Schrödinger's cats, but just think of my glasses. They could be here or they could be there. Now, classically, you think, okay, here or here. That's an or. But quantum mechanics says it can be in a state which is partly here and partly here at the same time. And the different ways, there's a whole lot of different ways it can be here and here. And all those different ways it can be here and here involve this complex numbers.
Penrose's motivation for Twistor theory is to formulate classical physics in a way which uses essentially these complex numbers. And in doing so, he produced what we would call the non-local theory. Let me explain that of physics. It's perhaps the more far-reaching departure from a notion of a point or an event as an elementary object in physics. What you do in Twistor theory, you assume that space-time points are not elementary, they are derived objects. What instead is fundamental are light rays.
So Twistor theory brings together ideas from quantum mechanics and those from relativity. And the basic thought is, okay, so what happens when you're looking at the sky? Well, it's a light ray coming and hitting your eye. So at one moment, I look out at the sky, and it's all the light rays coming into my eye. Imagine I could see all the way around myself. Then that light cone, as it's called, let me think of those light rays, instead of points as being the basic thing, the entire light ray is the basic thing. So I think of a space whose points are the light rays. I have to do a bit more, and I have to think of those light rays having a spin as well, which photons do. They spin about their axis. And there's a little more to the story. But what it turns out is these complex numbers describe that geometry completely.
Points and events in space-time correspond to extended objects, curves in the Twistor space, and conversely, points in Twistor space correspond to light rays or null surfaces in space-time. So it's a very non-local theory. A point is not fundamental.
So what you find is, amazingly, and it is really a remarkable thing, that the geometry of complex numbers describes this relativity picture in a beautiful way. And then you go and see how can you describe fields, Maxwell's beautiful equations for electromagnetism, gravity, at least in the limit of weak fields.
The physics behind Twistor theory despite some spectacular development in the last 10 years, is still not clear. What is the case is that there's been an unexpected spin-off in applications to pure mathematics. That's what made me interested in Twistor theory. You can solve many pure mathematical problems which at the first sight don't seem to have anything to do with physics. You want to solve nonlinear equations, build curved geometries. You can do it using this Twistor language. So it might be that there will be a connection between Twistor theory and cosmology, the CCC model, that hasn't been yet made clear. But it is fair to say that the development in conformal geometry, in pure mathematics, which made conformal cyclic cosmology possible, was driven by the early work on Twistor theory. It was then in the 60s, 70s, when pure mathematicians started learning from Penrose theoretical physics. They wanted to understand twistors because they realized how useful a technique it is for them.
There is this union between the idea of the complex numbers, which come from quantum mechanics, and feeding in to the structure of space-time. And that's what twistors do for you. Twistors is basically the twist that you get from the pattern when you consider spinning photons, if you like. That's what it comes from. Far from being a quantum gravity theory, it's not that. It's a way of looking at current physics, which is, there's a lot of work in high-energy physics now which uses Twistor theory. But I think there's a lot more in Twistor theory which has not yet been exploited, and which I hope new ideas in that area will enable it to be exploited, the subject to be exploited better. And there are ideas about how eventually you might do things like quantum gravity, but that's a long way off for the moment.
Most cosmologists think that in order to understand the Big Bang, we need a quantum theory of gravity. But CCC seems to sidestep this demand.
It's still classical geometry. You don't have to think about quantum mechanics. And people would say, well, surely the curvatures get so big that the radius of curvature gets so small that you're in this quantum gravity regime. But then I say now, that no, it's not that, because there are two kinds of curvature. One of the curvatures is what's called Ricci curvature, R-I-C-C-I, and that is the curvature that matter directly gives you, according to Einstein's theory. If you have matter there, you've got this Ricci type of curvature. That's 10 numbers per point, 10 components per point. There's the other part, which will give you the other 10, if you like, which is called the Weyl curvature, W-E-Y-L. Now, Weyl, Hermann Weyl, was a very great mathematician who got into studying general relativity very early and made some very important contributions that contribute to particle physics and so on. He's really a pure mathematician. But he understood about the curvature in conformal geometry. So when your geometry is the stretchy, squashy kind of conformal geometry, the curvature is just in this Weyl part. So what I'm saying now is that the Ricci part doesn't count. Once you look, see, the gravitational field is in the Weyl part. And that, as you go near to the Big Bang, it goes to zero. So it's not as though it's huge curvature, and in the Big Bang, it's gone to zero. It's nothing. So it's very classical from the space-time point of view.
If CCC can resolve the Big Bang singularity, can it also resolve the singularities in black holes?
No. I mean, this is a remark. You see, it's this whole thing. I used to say the difference between the singularities was to do with the Weyl curvature, you see. The Big Bang was very particular as a singularity, a singular place where curvatures go to infinite, if you like, and general relativity breaks down, but only mildly at the Big Bang, because it's only the Ricci part which goes infinite, and you can scale that away with the conformal scale. Now, in the black holes, it's completely the other way around. That is to say, it's the Weyl part which goes infinite, goes wild. And that's, you can't do anything with that. Stretching it out doesn't do anything. It's a mess. It's a conformal curvature. It's the curvature of conformal geometry. And that's what goes singular. So in the black hole, okay, maybe you need quantum gravity in the black hole. Yeah, but what do you do with it? Because it doesn't go anywhere. So it's a little disappointing from the point of view of quantum gravity, because, well, even if you had a good theory of what happened in the black hole, you'd be stuck, because it doesn't go anywhere. It goes Eventually, this black hole disappears by Hawking evaporation, goes off with a pop, and it's gone. Maybe you could study the pop at the end. Yeah.
By not using quantum gravity, CCC marks a radical departure from what most cosmologists think is needed for a theory of the Big Bang. But when dealing with the origin of the universe, maybe a radical departure is just what we need.